So this is a common question that students will ask or get a little bit stumped on. So first of all, this idea of a neutral ground state atom. What this is telling you is that we're basically going to follow the rules that we've set up in the past. Really what I mean is that it's neutral, so you don't have to worry about either adding electrons. So since it's neutral, we know that it has the same number of electrons as protons. So there's no guessing, there's no, well, maybe in some alternate reality they've got some other kind. No. You should be able to figure out how many electrons there are, because you should be able to look at a periodic table and figure out that how many protons that atom has, same number of electrons. So nothing special. Then, ground state. The reason why we talk about the ground state is because when we were talking about things like putting electrons in orbitals, you start low and go up from there. So this is the way we know that since we're in the ground state, we know we're going to start low, go high. We don't have to worry about something weird. So that's 1, 2, 3, 4, 5, 6, 7 electrons. Draw the next energy level 2. I'll put another one over there. So we don't have to worry about some sort of bizarre, excited state where electrons are just everywhere. So ground state tells us that it's not something strange. So this is our ground state. So ground state just simply tells us that we're going to start low, go high, things that we've done before. Now that we kind of have an idea of why those words are in there, which really is just a setup, we're going to follow the rules we've done before. Now we can actually deal with this n equals 3, L equals 2 mumbo jumbo. So to do this, we're going to need to take a look at what that means. So n equals 3 and L equals 2. So this is in the whole atom. Keep that in mind. So in the whole atom, if you have an n equals 3, you also have an n equals 2 and an n equals 1 that you have to deal with. So realize that in the atom itself, you have all the lower levels as well. But it has to be true. Both of these statements have to be true. So both n equals 3 and L equals 2 must be true. So the nice thing is, since you have an L equal to 2, that means that we don't care about these guys. Because when n is equal to 2, you can have an L equal to 1 and an L equals 0. You can also have an L equal, and only an L equal to 0 in this. So since we know L has to equal 2, we don't worry about the other ones. So they are there, they have electrons, but we don't care about them. We only care where n equals 3 and L equals 2. So let's take a look at that n equals 3 shell. So we are going to have a 3s, we will have a 3p, and we will have a 3d. S is where L is equal to 0, P is where L is equal to 1, D is where L is equal to 2. So even though we can talk about having electrons in all of these places, the only ones we care about in this case are where L is equal to 2, because we want both of these cases to be true. So all we care about then is this last setup. So where this is a neutral ground state atom, has to be described by n equals 3 and L equals 2. Here's my 3. So this is my n value. And here is my L equals 2 value. So the number of electrons that can be satisfied by that are the up and down arrows in my blanks here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So my electrons are equal to 10. So now let's take a look at the second one. So we still have those words, neutral, ground state. And we've already talked about what those words mean. So they're still there. So same rules apply. Now we have an n equals 4 and m sub l equal to 2. So again, since we are in an entire atom, we still have to worry about n equals 3, n equals 2, and n equals 1, because all of those are still there. But again, we know that m sub l is equal to 2, but this also then means that since m sub l is equal to 2, we also know that this is going to be an L of equal to 3 or an L equal to 2. Both of those cases will hold. So in that case, we can still have an L equal to 2 and an n equals 3, but not in any of these other ones. So we don't have to worry about n equals 2, and we don't have to worry about n equals 1. But we are going to have to worry about n equals 4 and n equals 3. So there are two different shells we have to take into consideration to do this problem. Now, since we have that, we're going to go ahead and start with the smaller one. We're going to start with our n equal to 3. We're going to come back to n equal 4. So when n equals 3, you have the 3s, the 3p, and the 3d. So here's my, again, my L equals 0, my L equals 1, my L equals 2. This is going to be my m sub L equals 0. Here my m sub L will equal -1, 0, and +1. Here my m sub L is equal to -2, -1, 0, +1, +2. Now realize that I'm going to go ahead and put those m sub L values under those orbitals. That doesn't necessarily mean that they go in that order, because those orbital lines are just a representation. So theoretically, if you wanted to put -2 and then +2 right next to each other, you can. This just looks more like a number line. It makes more sense to me. But the idea that each m sub L value gives you a single line, that part is accurate. So since we know m sub L has to be equal to 2, we don't care about S. We don't care about P either. But we do care about our D subshell. And we can go ahead and put our electrons in. And the number that fit in a 2 orbital are right here. So we can get 2 electrons from our atom of our n equals 3, L equals 2, m sub L equals 2. And again, I got my L equal to from m sub L. So since I know m sub L has to equal 2, I know L has to be equal to at least 2. So that gets me 2 electrons from there. But this is a whole atom, and my whole atom still involves n equals 4. So I have to look at my 4 as well. So I've got 4, I'm going to have 4s, 4p, 4d, and 4f. So again, here's my n equals 4 with all my 4s. Then that's L equals 0, L equals 1, L equals 2, L equals 3. Then my m sub L values, let's actually do those in another color. 0, -1, 0, +1, -2, -1, 0, +1, +2, -3, -2, -1, 0, +1, +2, +3. So I want my m sub L values equal to 2. So where m sub L is equal to 2, that's going to be right here and right here. And we could go ahead and put in electrons in all those places. So I know that was a lot of work just to show that where n equals 4, remember you have to take into consideration n also is equal to 3. So since you know that m sub L is equal to 2, we need all of the locations where you might have an m sub L equal to 2, which is n equal 4 and n equal to 3. The way I got my L equal to 2 is from my m sub L value, but realize that I have an m sub L equal to 2 where L is also equal to 3. So do realize that my m sub L value gives me a minimum value of L. So, but L can be equal to 2 or higher when I'm looking for my M sub L value equal to 2. So all it really does is it tells me I don't have to worry about my 4S or my 4P. S's and P's won't have an M sub L value equal to 2, so I got to ignore those. But I do have to worry about all of the other ones. So this kind of a question is one that I think takes more consideration than you might have originally anticipated. Most students want some sort of magical formula to deal with this, and there really isn't a magical formula. In order to do this problem, though, you have to combine what you know about electron configuration as well as what you know about quantum numbers.